So, here we're going to talk about ideas of risk and life expectancy. So, a smooth talking but honest salesman comes to you offering a new product. I can't reveal the details yet, but you will love this product. It will improve your life in more ways than you can count. Its only downside is that it will eventually kill everyone who uses it. Will you buy one? Not likely. After all, could any product be so great that you would die for it? A few weeks later, the salesman shows up again. No one was buying, so we've made some improvements. Your chance of being killed by the product is now only 1 in 10. Ready to buy? Despite the improvement, most people still would send the salesman home and wait for his inevitable return. Okay, this time we've really perfected it. We've made it so safe that it would kill only about 35,000 Americans each year, and it can be yours for a mere $30,000. You may be surprised to realize that if you're like most Americans, you'll jump at this offer. The product is, after all, the automobile. It does indeed improve our lives in many ways, and $30,000 is a typical price. However, about 35,000 Americans are killed in auto accidents each year. As this example shows, we frequently make trade-offs between benefits and risks. In this section, we'll see how ideas of probability can help us quantify risk, therefore allowing us to make informed decisions about such trade-offs. Are you safer in a small car or in a sport utility vehicle? Are cars today safer than those 30 years ago? If you need to travel across the country, are you safer flying or driving? To answer these and many similar questions, we must quantify the risk involved in travel. We can then make decisions appropriate for our own personal circumstances. Travel risk is often expressed in terms of an accident rate or death rate. For example, suppose an annual accident rate is 750 accidents per 100,000 people. This means that within a group of 100,000 people, on average, 750 will have an accident over the period of a year. The statement is in essence an expected value, which means it also represents a probability. It tells us that the probability of a person being involved in an accident during a single year is 750 in 100,000, or 0.0075 when we take 750 and divide it by 100,000. This concept of travel risk is straightforward, but we must still interpret the numbers with care. For example, travel risks are sometimes stated per 100,000 people, as above, but other times they are stated per trip or per mile. If we use death rates per trip to compare the risks of flying and driving, we neglect the fact that airplane trips are typically much longer than automobile trips. Similarly, if we use accident rates per person, we neglect the fact that most automobile accidents involve only minor injuries. Example 1. Is driving getting safer? So the figure shows the number of automobile fatalities and the total number of vehicles miles driven among all Americans for each year over a period of more than 4 decades. In terms of death rate per vehicle mile driven, how has the risk of driving changed? So in 1970, we can see that there are 52,000 deaths, and we divide that by a very, very large number, and that equals a death rate per mile of 0. We've got several zeros here, 52. In 2015, we have 34,000 deaths per even a very larger number of miles, and we end up with many zeros, 11 deaths per mile. So as we're comparing those rates between 1970 and 2015, note that death per mile is equivalent to 5.2 deaths per 100 million miles. We conclude that over the approximately 4-decade period, the death rate per 100 million vehicle miles driven dropped from about 5.2 to about 1.1. By this measure, driving became much safer over the period. Most researchers believe the improvements resulted from better automobile design and from safety features such as shoulder belts and airbags. Back in the days, in the 1970s, we didn't wear seat belts. And then when you did, you didn't have the shoulder part that went on them. I remember riding in the back of the car. We didn't ever put on our seat belts. None of the drivers did, and none of the passengers wore them. That came about in the 1980s. And there were no airbags back then. So which is safer, flying or driving? For the 11-year period from 2002 to 2012, the total number of deaths in commercial airplane accidents in the United States was 158. For an average, which is your mean, about 11 deaths per year. By the end of this period, the total number of miles flown by commercial aircraft was about 8 billion per year. Use these numbers to calculate the death rate per mile of air travel. So we're comparing the risk of flying to the risk of driving. So assuming that there were 11 deaths in 8 billion miles in an average year, the risk of air travel is 11 deaths divided by 8 billion miles, which gets us this death per mile. Oops. So we conclude that over the approximately 4-decade period, went back too far, sorry, the risk is about 1.4 deaths per billion miles, or 0.14 death per 100 million miles, which is only about 1/8 of the risk of 1.1 deaths per 100 million miles for driving, from example 1. So data concerning birth and deaths of citizens, called vital statistics, are very important to understanding risk-benefit trade-offs. For example, insurance companies use vital risk to assess risk and set rates. Health professionals study vital statistics to assess medical progress and decide where research resources should be concentrated. Demographers use birth and death rates to predict future population trends. One important set of vital statistics covers causes of death. The table shows the leading causes of death in the United States. A more detailed table might, for example, categorize the data by age, sex, and race. Vital statistics are often expressed in terms of deaths per 100,000 people, which makes it easier to compare the rates for different years and for different states or countries. Assume an approximate U.S. population of 325 million. Use the table to find and compare risks per person per 100,000 people for accidents and cancer. So first we want to find the risk per person by dividing the number of deaths by the total population, of 325 million. So accidents, we go over here to accidents, we can find there's 130,557 deaths. Out of that 325 million people, gets you approximately 0.0004 risk of death per person. For cancer, we find that there are 584,881 deaths for 325 million people. So the death risk is approximately 0.0018 per person. See, we're missing our squigglies right here. So this should be squiggles just like this, which means approximate. We can convert these numbers to deaths per 100,000 people by multiplying the per person rates by 100,000. We find that the accident death rate is about 40 deaths per 100,000 people, which is much lower than the cancer death rate of 180 deaths per 100,000 people. So one of the most commonly cited vital statistics is life expectancy, which is often used to compare overall health at different times or in different countries. The idea will be clear if we start by looking at death rates. The figure shows the overall U.S. death rate or mortality rate in deaths per 1,000 people for different age groups. Note that there is an elevated risk of death near birth, after which the death rate drops to very low levels. At about 15 years of age, the death rate begins a gradual rise. So at the beginning, you have a rate, and then it kind of steadies along, and then at about 15, when people start to learn to drive and start driving, and maybe are a little more risky with their behavior, then it starts to gradually climb up. So the figure shows the life expectancy of Americans of different ages, defined as the number of additional years a person of a given age can expect to live on average. As we would expect, life expectancy is higher for younger people because on average they have longer left to live. At birth, the life expectancy of Americans today is about 79 years, 76 years for men and 81 years for women. Life expectancy is the number of additional years a person of a given age can expect to live on average. So we can see at 0, they're expected at 79, and as you get older, the years you have left are going to gradually go down. So using that figure, find the life expectancies of Americans at age 20 and age 60. Are the numbers consistent? Explain. Well, the graph shows the U.S. life expectancy at age 20. Go up, it goes to 60. At age 60, it is about 23. So if we go up to 60 and come over, it's at about 23 years. This means that an average 20-year-old can expect to live about 60 more years to age 80. An average 60-year-old can expect to live about 23 more years to age 83. It might at first seem strange that 60-year-olds have a longer average lifespan than 20-year-olds. But remember that life expectancies are based on current data. If there were no changes in medicine or public health, a 60-year-old would have a greater probability of reaching age 83 than a 20-year-old simply because he or she has already made it to age 60. However, if medicine and public health continue to improve, today's 20-year-olds may live to older ages than today's 60-year-olds. So life expectancies have been rising with time because of improvements in medical science and public health. This fact leads to a subtlety in interpreting life expectancy because they are calculated based on current death rates. For example, when we say that the life expectancy of infants born in the United States today is 79 years, we mean that the average baby will live to age 79 if there are no future changes in medical science or public health. In fact, most people expect that life expectancies will continue to increase as public health and medical treatments continue to improve. Therefore, while life expectancy provides a useful measure of current overall health, it should not be considered a prediction of future lifespans. Example 5. Using the figure to estimate the rise in U.S. life expectancies during the 20th century, suppose that life expectancies rise by the same amount during this century. What will life expectancies at birth be for children born in the United States in the year 2100? What are the implications to your own life expectancy? And explain. So the figure shows that for women in the United States, women is the teal color, at birth rose from 48 years in 1900, here we can see it, 1900, 48 years, to about 80 years in 2000. Well, that's an increase of 80 minus 48, 32 extra years from the women born in 1900 to the ones born in 2000. For men, life expectancy at birth rose from 46 years in 1900 to 74 years in 2000. An increase of 74 minus 46 equals 28 years. In the same increase If the same increase occurs in this century, then in 2100, life expectancy for female newborns will be 32 years greater than the 80 years in 2000, which means it would be 112. Life expectancy for male newborns will be 28 years greater than the 74 years, which will mean it will be 102. In other words, if life expectancy in the United States advances as much as in the 21st century as it did in the 20th, life expectancy at birth will reach 112 for women and 102 for men. Note that although this example deals with life expectancy at birth, life expectancies for all ages, not just at birth, tend to rise together with time. Therefore, if life expectancies continue their trend from the 20th century, then there is a good chance that today's high school and college students will live to average ages over 100 for men and 110 for women.